Oh, last day's recording. I didn't upload that. Just wait. Possibly I haven't uploaded that. Okay, fine. I'll do that today. Okay. Fine. Anything else apart from that? No. Fine. Atri, good morning.
Sir,
Huh? Ananya,
I had doubt in a question. I have sent it in the group.
the group you sent it. Let's see. Wait, what happened? Variation of potential energy. Okay. Okay, there are a couple of things. You may be able to answer this question yourself. You see, we already have figured out the relationship between the potential energy and the work done actually. In fact, we determine the potential energy for a system of particles by looking at the work which has to be done in order to bring the system from basically infinitely far distance and keeping them at a certain location, isn't it? That's what the potential energy is. According to definition, if I just consider we had the potential energy for a system, it can be written down in effect as the work done for a just wait. I could write down this one as minus m into from the reference point to the certain point P, the force of the system into dl. That we could write down. The point is, oh sorry, it will be not m. The same won't be there. In effect, the point is that if I just O over here represents a reference point actually. This is the reference point. That is in effect the definition for the this is the forces or the field forces. As we have. This is the definition for the potential energy, where we in effect find out the work done of the external agent, but then the work done for the external agent is negative of the work done by the force whose potential I'm considering actually. For example, if I look at the potential for the gravitation force, I then have to just take something up over there. In that case, I'm doing the work. So my work will be equal to increment in the potential energy, or the negative of the work done by the gravitational force will be also the same actually. That is a definition for a finite path. What I can do is I could write down this one in a slightly different way. I can just look at the work done over a very tiny path, very small path actually. In which case that will be nothing but written down as d, which is the increment in the energy for a very small path. That has to be equal to minus f dot dl. Okay, this is the basic that I've taken a differential on both the sides, or simply utilize the definition of the increment in the potential energy for a very small path. It was same as the work done by the external agent for, over that small path. That is same thing as work done by me, negative of that actually. So if I write down this f dot dl, this I could write down as minus fl into dl, where as I already said, FL represents the component of the force in the direction of displacement. This one is the force component along dl vector, the displacement over there. Fine. So this I could write on a slightly different way. Okay, I could write on this equation as FL equal to minus del U by del L in this fashion. I've changed a couple of things. For example, I have written instead of D, del. This is the character which represents a partial derivative actually, which implies that it may happen that this potential energy will be dependent on uh, other parameters as well. But in this case, I'm differentiating partially with respect to L, which implies partially with respect to the displacement in which whatever direction it is actually. So it says therefore that if I consider the so the differentiation or derivative of u partially with respect to a certain variable. In that case, what I end up getting in this case is the force component in that direction actually. Okay, this L could be either the x-axis or could be the y-axis or any other direction. In polar coordinates, it can be either the increment in the distance dr or the displacement along the tangential direction. Whatever. The point is that if I just want to figure out the force, if I know the potential energy as a function of the coordinates, and I wanted to figure out the force in a certain direction, it is then enough to differentiate the potential energy with respect to the distance. Okay, that's one thing that we have. For example, if I consider the x-axis, if I if the displacement is along the x-axis, for instance, in that case, if x is becoming minus del u by del x. Okay, in similar fashion, we can obtain the force along the y-axis. It will be nothing but minus del u by del y. We differentiate partially with respect to y. I said when we differentiate partially with respect to a certain variable, everything else needs to be taken to be constant. Okay, say except for that variable, what? It may not have been logged in properly on it. Otherwise, yeah, it has been. It's okay so far. At least from my end, it is fine seemingly. Now it is okay. Things are coming up. That is fine. Okay. So this is what we have. This will give us the x component, and if I just do it along the y direction, we get the y component, and so on. So the idea is that if I know the force, so the potential energy as a function of the coordinates, in that case, I can definitely figure out the force itself. Okay. For example, if I in a similar fashion, I could get the y component, and I can also get the z component if it is required. It will be, if it's a three-dimensional situation, it will be fz as well. For two dimension, these will be enough. So in terms of them, I could write down the force vector itself in two dimension I'm talking about as minus del u by del x I cap minus del u by del y j cap. And if there is a z coordinate available, in that case, it will become minus del u by del z along the k cap direction. Okay. So given the potential, you can figure out the force vector entirely. Is it okay? That's a very interesting result by the way, because On one side, we require a force vector to be having three components. It requires three numbers over there. While on the other side, the potential energy is scalar, in fact, just one number. So how it happens that we're able to represent the same information which is contained in three numbers by using a single number, the potential energy. It turns out to be they're intricately related, but yes, but not in the usual sense of addition on it. It's not an algebraic addition, it is a vector addition. You just can't add them in the. For example, if I wanted, say, the potential energy U varies as K into XY, for example. We have already seen such a force over there. K into XY is a potential energy. Then I can obtain the X force as minus del U by del X, which implies to differentiate this equation partially with respect to X, meaning take K and Y constant. Because K and Y both are supposed to be constant, X is differentiated. So you end up getting nothing but 1 itself for derivative, and I end up getting minus ky therefore, and the y component will turn out to be minus del u by del y, which is minus k into x. So I know both the components, and therefore the force is known to us. Minus k into x I cap plus y j cap, isn't it? That is the force. I mean, the other thing, if you just keep, there's one more thing that we can deduce from the given expression that we have earlier written down. We have saw that du was minus fl into dl, or you can just write down this one as f dot dl, which we could write down as minus f into dl into cos theta, where theta is the angle between the force vector and the displacement vector. Okay, so I could see from here that if I move, say in different directions, say from one point I move in different directions over there, so that the angle between f and say displacement, that is going to change. F remains the same. I can see from here that if I from a certain point move in various directions, okay, I find if I just go this way or this way or this way or this way, in multiple directions I can have my displacement. So in those cases, what happens is if I keep the length same, dl same, then we end up getting what? We end up getting the dl is, so dl length is same, but theta might be different. So f cos theta will be different as well for given f actually. If I just fix f over there and I just change my direction of the displacement, this will be then the minimum. Or say if you look at du, the increment is the most negative actually when cos theta becomes 1. The increment is most negative when cos theta becomes 1, implies that the decrease in the potential energy is the largest when my force and displacement are parallel, isn't it? Which implies I could see that for a given variation of potential energy, the force is directed in that direction where there is the greatest amount of decrease in potential energy for a certain displacement, isn't it? From here, what you end up getting is du is minimum because there's a negative sign. It's minimum in the direction of the force. For a given displacement, actually, it also means therefore that the force is going to be pointing, is directed along the direction. I hope it is visible enough or readable at least. So the force is directed along the direction in which there is largest drop in the potential energy for a given displacement actually. So it will be directed in that direction, I can start from one point and try to move in various directions. Okay, I just try to move in various directions for the same amount. Then whichever direction it turns out that the decrement in the potential is largest, that will be direction of the force itself. Okay, this gives. Uh,
The force it is written U.
uh, I'm reading it. The force is directed. Is. This is bad handwriting.
Okay, sir. Okay, sir. Okay.
The force is directed along the direction in which there is a largest drop in the potential energy. The force is always directed in that direction in which the decrement in the potential is the greatest, actually. Is it okay?
So we can
Okay.
use the formula means du equals to minus f dot dl only when the force is conservative, right?
The potential energy concept is defined only for conservative forces. We cannot have the concept of potential energy for non-conservative forces. Actually, we said that earlier. It will be defined only when the work is independent of the path chosen. Actually, yeah, it's valid only for such forces. But as it turns out, many forces of that kind, in fact, only it happens that when some forces, usually when some forces depend on the velocity, it is no longer conservative. Otherwise, most of the forces which depend only on distances or only the position rather, they will be conservative in nature. Friction is not definitely conservative. Now we could just look at coming back to this equation over there once again, but this time we do it in the one dimension. If I consider in one dimension only, there is no need of the partial derivative. There will be complete derivative in fact. So in one direction, or one dimension rather. If we write down, for example, I'm just dealing with the x-axis, for example. It could be any direction. It could be radial distance, x-axis, y-axis. I'm just writing fx, but it doesn't mean that it has to be along the x-axis only. It can be in the y direction as well, or any other direction actually. Fine. So I could write down fx as minus du by dx. In this case, there is no need of the partial derivative because there is no other parameter. There is no other variable. Only one coordinate is there. So we have got this. From here, we can just observe a couple of things. You notice that if I am able to draw the graph of du by, the potential as a function of x, then at any point, if you draw the tangent line, negative of the slope of the tangent is same thing as the force in x direction. This gives therefore that the force along the x-axis from the graph, in fact, negative of the slope, negative of the slope of the tangent drawn to the curve of, drawn to the graph of, drawn to the graph of actually. Potential energy versus x. If I will draw the graph of potential energy versus the position, in this case the x coordinate, negative of the slope of the tangent drawn to the graph of u versus x will be equal to the force component along the x-axis. The force component along the x-axis. We have this useful result because the negative of the slope of the tangent drawn to the graph of u versus x is equal to the force component along the x-axis. Okay. So if I just consider, for instance, that there's some graph of the potential energy versus x, then it will be easy to determine that this is a variation of u, for example. This is just an example, though it is a very common kind of potential energy graph that we have usually. It appears in a lot of positions over a lot of cases, in fact, or situations. As it turns out, this kind of potential energy uh, does estimate or does kind of represent the intermolecular forces as well between the particles of a substance. Usually, this variation is this kind. It also comes up in other situations. For example, in gravitation, if I consider the potential energy of the planets in a rotating reference frame, it turns out to be exactly the same way. In fact, this kind of graph is also true for not only intermolecular forces, but also the internuclear forces actually. It turns out that even if I just look at the variation of the nuclear force, which is within the nucleus, the shape is pretty much like this. Okay. Now, first of all, a couple of things can be noticed for this kind of potential energy. We already have seen that at any point, if you draw the tangent at to the graph of this potential energy curve, the slope or negative of the slope is actually equal to the fx, the force component, isn't it? So if I look at in this case, for example, a couple of things that we notice from here is that if I look at this position over there, lowest position, the lowest position of the potential energy curve, the tangent is horizontal in fact. The tangent is horizontal, which implies that the slope is zero, which implies this has to be this tangent is horizontal, which implies in this case that this must be the point where the equilibrium is there. Equilibrium implies net force is zero in this case, because the tangent is horizontal, implies the slope is zero, and therefore the force is zero as well, which implies this must be the equilibrium position. Okay. Now, before, if I look at the left side, for example, on the left side, any point I consider this way, for example, at this point, if I look at the tangent will be like this, the tangent is this way, which implies it has a, this is a tangent line at this location over here, at this x over there. At this particular point, the tangent is inclined at an angle which is more than 90 degrees, in fact, with respect to the positive x-axis. Therefore, the slope is negative. Tan of the angle which this line forms with the positive x-axis is more than, means a negative. Slope is negative implies the force is pointing in the x direction, which implies the force is positive, which implies the force is in fact acting towards a positive x-axis. So it's kind of a repulsive force actually. Whatever is sitting at the origin is trying to repel the other particle which is trying to come nearby. Fine. Therefore, if we just go, say at a distance less than the equilibrium position, what I find is that the force all around is in fact positive, which implies a repulsive force. This one is negative slope, negative slope, negative slope, negative slope always. So the force is in this case repulsive. It tries to just push the other particle away from the origin. Okay. On the other side, if I go to the right side of the equilibrium position, like this one, for example, at this location, the tangent is actually like this. So it has a positive slope. So positive slope, it implies that the force is on a negative x-axis, which implies pointing this way, meaning there's an attractive force. So the force behaves in this case in the following fashion. If the particles are separated by a distance less than the equilibrium distance actually, in that case the force between them is repulsive. While if the separation between them becomes more than the equilibrium distance, in that case the force becomes positive. Right at the equilibrium position, there is no force at all. So this is the kind of force that we have mostly between the molecules or the particles of all the substances. In fact, let me say, for example, liquid or solid or gases. If they go too close, they are going to repel, but if they become too far, they're going to attract. That is what the behavior of the forces is. Now, without knowing much about the dynamical system, we can conclude quite a lot regarding the motion of the system over there. So, first of all, Rene, your question. Can you answer in this case what will happen to your question in this case? Because if you just, there's one more thing by the way. You should notice that if we consider the object to be located at this position XE, in fact, I mean this middle, the equilibrium position. And if I just shifted it towards the right slightly, if I just move it towards this way, towards the right, then the moment I release the object, there will be forces which will be attractive in nature, trying to bring it back, isn't it? Okay, just wait. If I just look at the total mechanical energy, there's one useful thing, something useful we can obtain from this graph without knowing much about dynamical system. What we know is that since the mechanical energy, if there's no work being done, I mean, in any case, the mechanical energy is nothing but K plus U actually. K is the kinetic, U is the potential, isn't it? A couple of things in this case could be seen. For a given energy, first of all, if the total mechanical energy is a given quantity, for example, in this case, let us say that this is the total energy. The value of the total energy that we have supplied to the system is positive. Say the value in this case is this much. This is the total mechanical energy, for example. With this mechanical energy, what will be the it will be something negative. You can see it's a repulsive force because at this point over the axis intersecting the tangent is still negative, isn't it? Slope is still negative for the tangent line. So the force is still repulsive, okay, in this case. At all points, wherever in this case there is a negative slope, the force is positive, which implies a repulsive force, in fact, along the positive x-axis. Okay. Yes, if I just look at this particular potential energy, the total energy, what's going to be the motion of the system? If it depends where I'm releasing it actually. If I release it at, say, for example, this point with this much of energy, it basically implies we're going to throw it actually, because at this location, for example, the potential is negative, this much. The graph gives the potential energy. So I see in this case that if I look at the kinetic energy, it is a difference between E and U, which implies that this location, for example, this length is the potential energy, which is already negative number. So negative of that becomes positive number, and E is this much. So in effect, this height between the total energy and the potential graph, this gap is in fact giving us the kinetic energy over here. This is the kinetic energy, the gap between the potential energy and the energy at any given point. We can also see from here in this equation that since K needs to be positive, kinetic energy cannot be negative. It is half mv square, can't be negative, which implies therefore that the object can be found at only those locations. Therefore, the object can be present only in those regions where E is more than equal to U. So graphically, it will be at only those locations where the graph of the total energy is above the potential energy. Graph of the total energy is above the graph of the potential energy. That's readable. I've written down this case, the object can be present only in those regions where the total mechanical energy is more than equal to the graph of the potential energy, in fact. In this case, for example, for this energy, given that we have been given, you notice that the particle can be only found till this particular position, this one. Because to the left of this position, I find that the graph of the potential is above the graph of energy, which cannot happen because then K will become negative. So in this case, the particle can be found wherever it's moving actually. It will be still have to be beyond this particular point. It will be on the right of this point, cannot be to the left. Okay. It depends exactly how the system, how the particle behaves will depend on where it has been projected. For example, if I throw the object at this from here towards the origin. From this position, I just throw it towards the origin. Fine. Towards the other particle actually. The other particle is sitting at the origin. So what will happen then? I find that it will start moving this way. Right at this location, however, the force you can see the tangent is positive, which implies the force is negative, which is an attractive force actually. So this is going to be attracted. It will be attracted towards this direction, towards the origin. So it will accelerate. In fact, as the time passes by, it will go this way because the force is acting that way. So it will actually accelerate. It will accelerate. As it accelerates, the gap between the energy and the potential keeps on increasing, which implies that kinetic energy increasing as well till it reaches the equilibrium position, at which point the kinetic energy is the maximum because then the gap is largest as well. After that, because it already has some energy, it will overshoot, it will come this way. But the moment it comes towards the left of the equilibrium position, now I find that the potential start decreasing. The reason is quite obvious. The tangent at this point will be negative, the force will be positive, it is now repulsive, which implies that this particle is being repelled now once it goes to the left side, okay? And therefore it gradually slows down. As you could see, the gap between E and the total energy, mechanical potential is decreasing. Ultimately, it just comes to zero at this point, which implies that this particular point over here, this location on the x-axis, the velocity turns out to be zero. The kinetic is zero. The particle comes to rest momentarily. It will come to rest momentarily at this x over here, because at that point the total, the kinetic is zero, but it will not continue to be at rest. Why? Because at this point there is in fact a force acting. The tangent is negative, so force is positive. So it's actually feeling a repulsion. So it will just be repelled that way. So it will start moving this way. Again, the energy increases, becomes maximum, then just start decreasing. But in this case, once it comes this way, there's nothing to stop. So it'll just go back. So it'll continue to move because there's nobody going to stop in this case. Though the force is repulsive in this case, we can attractive, but I see that the finite amount of kinetic energy is positive. It cannot stop actually, and because it can't stop, it just continue to move this way till infinity, never to return back actually. That is the motion in this case. If we throw it towards the origin, towards the other particle from this location, that way, it just reaches closest distance, then returns back, never to come back because the repulsion is too large. In fact, the energy is positive. Okay. So that will be the behavior in this case where energy is positive. What if the energy is negative? Or say, for example, it will be also same behavior even if the energy is zero actually. Even for zero, even for zero energy, implies I just release the object at rest at some location. Same kind of behavior. If I release at rest, for example, at this location, it will be pulled gradually. So kinetic increase. In that case, obviously, the energy will be let's see, zero energy. Wait. If the total mechanical energy is zero, what happens then? Straight. For example, let's look at this. Your total energy is zero. Then what happens? Zero energy is over here. That is also the energy axis over there. This is happened. The value is zero in this case. So for this situation, what happens? If I release at some point, for example, over here, then again it is experiencing an attraction because it is to the right of the equilibrium position. So what happens is just keep on accelerate this way, start moving this way, accelerate, and as it accelerates, the total energy, the kinetic energy increases till it reaches the equilibrium position, at which point the kinetic energy is maximum. That is the point where the force is zero actually. But the moment it reaches crosses the other side, now the force is repulsive and so starts decelerating. So just keep on decelerating till ultimately it reaches this location, at which point it's momentarily coming to rest, but then will not remain at rest because the tangent is in fact negative, the force is positive, so being repelled actually. So just repel, it'll just start moving this way again. It'll start moving this way, the kinetic energy increasing, attaining a maximum value, then again start decreasing. but again will not come to rest on that side because so the energy is always going to be there something. So it just continue to move away, never to return back once again. That is the behavior if I release it to rest some point over there. Fine. But what happens, for example, in the second graph, what you have written starting with E. E is equal to 0 actually, sorry. I've written down E is equal to 0, which implies the total mechanical energy is 0. That's what I'm taking the case as. Okay,
Okay, sir.
fine. If the more interesting situation is when the energy is negative, in fact, what if the energy is negative? If the energy is negative, then we could see that the motion of the object is bounded, in fact, in this particular graph at least. This is true for this graph, not true for any other graph. It is depending on the graph over there. Second graph, once again, the answer is exactly the same thing that we have in the first one. I just said in this case that the energy is 0, the mechanical is 0, which implies you can just think of it this way that at any point, the total mechanical is 0, implying that the sum of kinetic and potential is 0, in fact. So very far away, actually, if I think of this way, very, very far away from the origin, I just leave the object at rest effectively. You notice that as x approaches infinity, the potential tends to 0 in this case, actually asymptotically going to 0. It gradually reduces, ultimately we go to 0 when x has become very, very large, positive infinity, fine. So if in this case, what I said is if I just release the object at rest from very, very far away distance, so that the total energy is equal to the kinetic energy in that case, 0 actually, because at infinity there will be no potential energy and we'll leave it at rest, so there's no kinetic energy as well, which implies the total energy is 0 in this case, fine. So in that case, it'll take long enough time because very, very far away the graph is almost horizontal. It is not completely horizontal, but almost horizontal. Therefore, there will be a small amount of force acting, will be attractive force because it is at the right of the equilibrium position, will be attraction. The slope is positive, so force is negative. But it will be very, very small force actually. Nevertheless, given enough time, it will attract the particle gradually. So the particle will come closer, and as it comes closer, we see in this case that the gap between the potential energy and the E actually, what parabolic path the orbital show back. Yes, that's correct actually. That's correct, Shubham. In fact, that is what happens in SHM actually. For the simple harmonic motion, the potential is parabolic in nature. Fine. In this case, therefore, what happens is as the object starts coming closer because of the attraction, initially it will just move very, very slowly, but gradually as it comes nearby, the speed increases. And you could see that as it comes this way, the gap between the mechanical energy E and the potential energy, which is the given graph, it increases the gap. As the gap increases, so does the kinetic energy between of the object, because this gap does represent the kinetic energy itself. So the kinetic energy is therefore the gap is kinetic energy. Okay. So as the object comes nearby, the kinetic energy increases. It implies basically because of the attraction it feels. So being attracted, so it just continuously accelerates over there. The speed increases, the kinetic energy increases as well till it reaches the equilibrium position. When it reaches the equilibrium position, at this point of time, the kinetic energy is the largest actually. The force is 0 at this particular point, it will not be coming to rest at this location because it have already some energy, so overshoot. It just goes this way. As it goes this way, now it feels a repulsion and therefore it starts slowing down. Slows down till it reaches this location. At this point, the kinetic energy is 0 because the gap between E and U is 0. And so it is momentarily at rest at that location, but it will not continue to be at rest because there is a force acting which is repulsive. So once it comes to rest, it will be again pushed that way and will be repelled. So it will just start going that way, kinetic is increasing, reaches a maximum, then decreases, but then it will never come back because the force is not enough to hold it back. But so just go back to infinity and then stop. Obviously, the same phenomena can start, but in this case, it will be difficult because the force is unable to, the potential is not able to get to 0 ever, in fact. so it'll never return. In fact, okay. I was saying that say what happens if the energy is negative? If the total energy is negative, for instance, maybe across a different graph. The total energy is negative, then the situation is
So, sir, can we tell that where the kinetic energy is maximum, the potential energy is minimum?
for a
Means
given
if
amount
we
of energy, for a given amount of fixed mechanical energy. If the energy is fixed, then it will happen definitely that wherever the potential is least, the kinetic is maximum because the sum has to be a constant number. Okay.
Okay, sir.
Yeah. In this case, if I consider a negative energy, for example, the energy is negative, which will basically mean in this case, how can it be given is that we can release the object at rest, for instance, at one of these locations. This one, let's call it x1 or this one. If I release, this E is negative in fact. This is total mechanical energy, but it is negative. This can be done, for example, if I simply release the object at rest at one of these locations, either x1 or x2. In that case, at those locations, because I've released them at rest, there's no kinetic energy. So whatever is the mechanical energy is equal to the potential energy. Because it's negative, the potentials are negative as well. Fine. Now what happens if I release it at x1, for example? If I release the object at x1 at this moment, at this location, what happens? They're experiencing a repulsive force. The tangent is negative, force is positive. It experiences a repulsive force, so it starts to move that way. Again, because there's repulsion, so it starts to move towards the right. But as it goes that way, you could see that the gap between the kinetic and the potential, energy, so mechanical and the potential, this gap, this increases, which implies the kinetic is also increasing. That is, this gap represents the kinetic energy. This will keep on increasing till it reaches the highest value at the equilibrium position, which implies the equilibrium position will be moving fastest actually. And the moment it crosses the other side, it starts now feeling an attraction. So because there's attraction now, then what happens is this kinetic energy starts decreasing in fact till the object reaches the position x2, at which point the kinetic is once again zero. Fine. So it will come to rest momentarily. But again, because there is an attraction at that point, it won't be continue to be at rest. It will be then pulled inwards. So it starts going this way. Again, the same story. The kinetic increases till reaches the equilibrium position, but again starts slowing down, coming to rest at x1. This cycle therefore continues. It will start from here, it will go this way, accelerate, reaches the maximum energy over there, then goes that way, retard, slow down till x2, goes this way, again, so keep on oscillating. This one is therefore a situation where the object keeps on oscillating between these two locations actually. Okay. So the graph is not necessarily parabolic one, and the motion is not SHM, but it will be definitely periodic oscillation actually. Okay. There is a situation when we have the energy to be negative. For this particular graph, obviously, it is not always it's not a universal truth. The graph may be different. We can have, for example, a graph where the potential energy is simply behaving, say, for example, and this is obviously an idealized one, but I may have a graph of the potential energy versus the x coordinate, which is, say, for example, looking like this, for instance, like a well. This is simply zero. So what happened in this case is between these two locations, A and B, for example, what happened is that in between them, the energy potential is negative, but beyond that, it is positive, but it's a constant. In this case, obviously, the force is always zero. By the way, you can see this case that the tangent is always zero, which means that if I look at, the tangent is horizontal at all locations. So this particular potential energy does not generate any force at all. It is just simply zero, fine, always, because this tangent is horizontal. So the force is always zero. But we do have in this case piecewise constant potential energy as well. That's present in this case. So if I, in this case, release some object at rest no energy at rest, anywhere I release it, for example, I release this location at rest, in that case, not going to move, because in this case, the energy, in fact, for a given energy, we can see that it can be, if the energy was zero, for example, I simply keep it at rest. Some zero implies what? The E will be like this, horizontal. In that case, can be only be found in between this region, A and B, because only then the graph of E will be above U actually, isn't it? So at least this kind of force is obviously not going to be seen in a physical world. But the point is, for this kind of potential energy, for any given amount of energy, which is kind of less than this value, the total, I mean, the particle can only be found in between A and B actually. It's pretty much like a box actually. It's one-dimensional box. The object can only be found between A and B as long as the total energy remains less than this value, this value. But once it is beyond that value, for example, this one, then it can be found anywhere else actually. It will be, you just keep, obviously it is positive energy. This one, Shubham, I said in this case that for this particular graph where U is a piecewise constant function, in some portions a positive constant, some other parts negative constant. In this case, because the potential is always constant, which implies therefore there is no force at any point. There'll be an abrupt change in the force actually, right at A and B. But apart from there, any other place we consider, the net force is zero in fact, because the tangent is always horizontal. So in this case, it will be zero force always, which implies if I keep it anywhere, it will not experience any force. So it will continue to be there. That's an example of neutral equilibrium in fact. Okay. So, but in this case, one thing is quite sure enough. If I consider a given amount of energy, which is, say, for example, less than this value is called as U naught. So if I consider the value which is less than this value, like this much energy, for this energy, you can see that the particle can be found only in between A and B, because we need to make sure that the total energy graph is above the potential energy graph whenever the particle is existing. So it can only exist in between A and B, because in that region, the energy is above the potential energy. Okay. If I just leave it at some other point over there, obviously for this energy is a positive energy, which implies at any location I consider. For example, I can't leave the object over here, because in this case, the graph of E is below that of U, which implies if the particle can be somehow over there, it will have a negative kinetic energy. It can't happen actually, which implies the particle can't be found in this region or this region. It has to be somewhere in between them over there. In fact, if I leave it over here, for example, with some positive energy implies what? Because energy is positive, but potential is negative, it must be thrown with some velocity. It must have some speed at this location, which will be nothing but the kinetic energy will be simply the gap between the two graphs. In this case, the kinetic energy will be this much. So it implies that we need to throw it with some speed. Maybe if I can throw it towards the negative x-axis, it will continue with a constant speed. The energy will never change, the kinetic energy. It will move with constant speed till it reaches this location. At this point A, it actually encounters an impulsive force in a backward direction, because you can see from here to here, the potential rises abruptly, which implies we have actually in this case a potential barrier kind of thing. In reality, it'll never be like that. In reality, we can approximate this curve by a slightly slanted curve actually, with a very steep curve in that, because we can think of the straight line as if it was a limiting condition of a very steep line, which is it's like almost very steep. A line which is almost tilted roughly at 90 degrees, so the tangent is infinite. Tangent is infinite, the force is also infinite actually, which is undefined strictly speaking. It can be thought of like a wall over there. You throw something towards a wall, it just quickly rebounds. The wall hardly happens anything that. Something over there is like this. So when the particle goes this way, strikes it momentarily, it just switches the direction momentarily, because you can see what happened in this case is a very large impulsive force acts actually. So it'll just go back and start moving this way, but reaches the position of B. Again, the same, a very large impulsive force returns back. So it'll keep on oscillating between two, but this is no longer something like a SHM, but rather more like a ball bouncing, say between two walls actually, fine. Never to come to rest, no loss in energy, continue to do that, fine. That's what happens in this case. But obviously in this case, if the energy is above this value over here, for example, Then it can be found anywhere. In that case, you can think of like, okay, we just throw the object at this location. You start moving at a certain speed, and then the speed increases abruptly, but it crosses the wall effectively. Okay, that is situation in this case. This kind of force we have, this kind of potential energy we have. The force is always zero, but the kinetic energy can change depending on where the object is located. Actually, okay. These can be at least seen without in any other kind of knowledge regarding the system over there. We do not know what kind of system we have, but if we know about the graph, about the the potential energy variation, then we can see exactly what's going to happen over there. Anna? Okay.
Sir,
Huh.
sir, is the second graph related to the PWM signal?
What curve?
Sir, is the second graph, sir?
Second implies what? That
That
right one, left one.
sir, sir, the left one.
This one.
Yes, sir.
So what did you say? PW?
Sir, is it anyway related to the PWM signals curve?
Right now it's a potential, it's not a voltage signal. PWM is a pulse width modulation that appears for electrical signals only. It is not related at all. It is simply the potential curve.
Oh,
Okay,
okay, sir.
fine. Regarding what do you think, Ananya? Can you now do the question that you have asked? No.
Yes, sir, I'll try it out.
Okay, you can see a couple of things. For example, you can see that wherever the potential graph attains, this one is I have shown only one special graph, but obviously it can be any other kind of potential curve. For example, it could be what you have shown. For example, if I have a potential curve, which is, say for example, starts at say it is like this. For example, if I have some potential curve like this, looks like a hill. In fact, what happened? We can see at something regarding this one. For example, you notice at this point the tangent is horizontal. That is implying the force is zero. This is a point where the force is going to be zero. This one at point 1, then at point 2 as well, the force is zero. The point 3 also the point is zero. Force is zero. The point 4 also the force is zero. At these locations also the force will be zero. So at all points where tangent is horizontal, the force will be zero. Fine. So they are equilibrium positions, but they're different kind of equilibrium positions, not the same kind. For example, at this location over here, I see there's say force is zero indeed, but what if I shift the object slightly? At this point, the force is zero. If I keep it at location, it will not move. It will be at equilibrium. But what happens if slight disturbance causes it to move towards the right? If I move towards the right, for example, now that the tangent is negative. Negative tangent implies a positive force, isn't it? Positive force implies repulsive. So what happens is just experience a force this way, towards the right. So just continue to move that way, never to return back. Just go away, not to come back. Fine. Same thing if I displace on this side also same behavior. The tangent is now positive, the force becomes negative. Negative force implies this direction. So just go this way, never to come back again, which implies an unstable equilibrium. In fact, whenever we have a local maximum for a potential energy curve, that represents an unstable equilibrium actually. Fine. Similarly, if I look at the position number 2, for example, the lowest position, there the force that's a say equilibrium position as well. But if I displace it slightly towards the right, I find that this is experiencing a negative. Slope is positive, so force is negative, which implies the force is pointing towards the left. So if I displace it slightly in this direction, it experiences a force this way, tries to come back. If I displace it this way, the force is actually, slope is negative, so force is positive. It experiences a force towards the right, which implies that if I displace it a bit more towards the, right of the point 2, it experiences an, say, attraction. To this way, it experiences repulsion, not repulsion again, it will be at least around this point based on attraction, though along the x-axis the force is positive. But about this location is going to be almost like an attraction. The point is that the force is appearing, which will try to bring it towards its initial position. When that happens, you have a stable equilibrium actually. Yeah. So stable equilibrium implies that the first of all, obviously we have an equilibrium position. The force has to be zero. But if I displace it from that particular position, then forces will arise which will try to bring it to the original position actually. When that happens, we have a stable equilibrium. Yes, like a ball in a hemispherical ball, which is, say, kept at the bottom. But in fact, this says those graph of potential is pretty much looks like the behavior of an object on a surface, on a certain container, in fact, like a hillock, for example. So in this case, the stable equilibrium positions are this one, and this one as well, this one as well. Wherever there's a local minimum for the graph of potential energy, that represents a stable equilibrium actually. Fine. Unstable for a local maximum, stable for a local minimum. On the other hand, what if the graph was flat? For example, if I have for this portion, if I make the graph a bit flatter over there, say just goes this way, then it becomes almost like a plateau and then comes down again. In this situation, if I look at this point, for instance, then the force is quite obviously zero. But if I displace it, the tangent remains horizontal. Therefore, there is no force arising, in fact. So the force is zero. And apart from there, even if I displace it, there is no force arising to bring it either towards its original position or take it away. There is no force at all. And that implies that's a neutral equilibrium, in fact. This is an example, neutral equilibrium. Exactly, that's what we have. So we have in this case stable, we have unstable, and we have neutral. We can talk about something called metastable as well, which will be but I said, first of all, for any kind of equilibrium, the force must be zero, isn't it? Only then we can have equilibrium over there. Now, the idea is that if the force is zero at some point, and if the system is displaced from that point, then some forces are arising, which is trying to bring the system back to its initial position. If that is happening, then we have a stable equilibrium actually. So a stable equilibrium will be when once displaced from the equilibrium position, restoring forces arise, they try to restore the system. Then we have a stable equilibrium. But for unstable, the forces which will arise once we displace it from the equilibrium position will always tend to take it away from that position. Then we have an unstable equilibrium actually. Fine. While if the equilibrium is there and then once displaced, no force arises, in that case, we have a neutral equilibrium over there. Is it okay?
Yes, sir. Sir, but with respect to that local maximum and local minimum, when can we say there is stable and unstable equilibrium?
Well, at local maximum is unstable equilibrium. Local minimum is stable equilibrium. Okay.
Okay, sir.
Okay.
So, sir, when double differentiation of potential energy with respect to x is greater than 0, we have stable equilibrium, and when it is less than 0, we have unstable equilibrium.
Again, that's correct. Yes, if the graph is differentiable, yes, then. If it's twice differentiable, then obviously the first derivative should vanish, and the second derivative is negative, in which case it will be local maximum. And if the first derivative vanishes, second derivative is positive at certain point. That's local minimum, in fact. Okay.
Sir,
Yes.
what is the meaning of local over here?
Local implies with respect to the values nearby. We may have, for example, a local minimum more than a local maximum. For example, if I take up a graph like this, for example, say the graph is like this. This is a what is it? I said what? Okay, slightly different one I want. Just wait. Okay, what? Just wait. What I wanted is local minimum to be greater than the local maximum. Fine. So that way drawn earlier actually. That is a local minimum, and we can have like this, for example. For example, in this case, this is a point of local maximum. At this point, whatever the value is, it's lesser than this value. This value is positive. This is negative value. This is local minimum. This is local maximum. Local minimum is above the local maximum actually. Fine. It actually implies compared to the values in the vicinity, in the nearby points. It doesn't look at the graph in a global scale, but only around that point actually. That's what meaning is. Around the point if the values of the at certain point is below other values, that's local maximum, and similarly for the local maximum. Okay.
Okay, sir.
Apart from local, we also have global maximum minima, but they are not to be considered right now. They're not important as such. Global points don't require in this case. We just require the local points of maximum minima. Okay. And I can actually attempt your own that particular question you gave that to be attempted now at least. I mean, without knowing anything about a dynamical system, we can deduce so many things from just a graph of energy, the potential energy. In fact, that's an interesting thing. But obviously, it will be there only when the potential is defined, which is going to be when the force is conservative in nature, actually. Okay. Otherwise, it can't be defined over there. Okay.
What is the value of double differentiation of potential energy with respect to x-axis in case of neutral equilibrium?
0. It will be 0. The first derivative is 0. The second is also 0 actually at neutral equilibrium. Okay.
So consider one case means total energy means mechanical energy is 0, and at a certain point the potential energy is also 0. So can we consider that point as one of the end points of the means path of the motion of a body?
End points. Actually, if the total energy is 0 and the potential is also 0, then the kinetic energy will also be 0 at that point. Yes, you might actually depends on the graph. In fact, around that point, if the slope is 0, then it will continue to be at rest over there. But if at the, if I just look at the point where the graph is cutting the, let's say for example, the graph is like this, for example. Then this point, and if I have supplied 0 energy, the total energy is 0, we just keep it at rest at this x, for example, this x1, for example. And that will be not continue to be at rest. It will actually facing a tangent will be this way, which will be positive slope. So force is negative this way. It will start coming back. But yes, it may be thought of as one of the endpoints of the motion actually. Okay. Internal forces may be present, which is meaning of Shubham. What does mean? Internal force may be present, yes, definitely, but we've already seen that for a system, the internal forces, well, they can, say, affect the energy if they're dissipated, but otherwise, internal forces can't affect the energy. Okay, Shubham? Yeah. Anything else regarding this particular fact? Nothing. Okay, fine. You see, normally when we would have to work applying both the ideas. We have to mostly work together using the energy conservation principles and the momentum principles as well. Together, they become very powerful in solving most of the questions. In fact, obviously, in many cases, we need to revert back to dynamics over there. But as long as the conservation laws can be applied, they should be the one which have to be applied. Actually, you should just try to think the first instinct should be to apply these conservation laws. If they're applicable, they will give the required answer quite easily over there. But if they're not applicable, then obviously we'll have to go and look at the forces. However, the strategy for solving a problem, obviously in an unknown situation. Right now, obviously, you'll get questions which are in certain context. You already know what has to be done. But for the exam setting, for example, when you do not know where the question is coming, the first thing or first idea or first instinct should be to think about the conservation laws. If they are applicable, they will give the required answer very easily, by the way. For example, if I consider, say there's a wedge which is in shape of a hemispherical object together with a slab around it. I'm saying this is a wedge kind of, a cylindrical wedge might consider. or a spherical wedge. We have basically a rectangular block, a cubical body from where a spherical portion has been scooped out. A hemispherical portion has been scooped out actually. That is what we have such kind of wedge in this case. Uh, Say that there's no friction at all, everything is frictionless. The hemispherical portion over there has a radius which is equal to r. This mass is m. It actually can move on a frictionless surface. The surface is frictionless. There's no friction anywhere, in fact. And there's a small object released from here. This point A, I release a small object whose mass is m. The object is small, the mass may not be small. So from the point A, point mass of mass small m is released at rest. There is no friction anywhere. So what will happen in this case as this object slides down? There is no friction anywhere over there. So as the object slides down, this will also move, isn't it? Capital M can also move with it. So what do you think? What will be the speed of the wedge? The speed of the wedge when the small m has reached the lowest point over there. When the small a has reached the lowest point, what will be the speed of when the particle of mass m has reached lowest position on the hemispherical wedge? Determine the speed of the hemispherical wedge. Determine the speed of capital M, I can say. Yeah. How to do that? We have in this case, obviously whatever we have discussed so far will not be applicable over there. It is simply a, I must say, application of the energy and the conservation principles, momentum principles actually. We release this object from rest over here. There is no friction anywhere. No friction anywhere in this case. So as the object starts sliding down, what will be the speed when it reaches the lowest position? That's the question. Okay, sure, I'm waiting. I'll just drink some water.
Sir,
Someone was saying something? I was not here. Nothing.
sir, can you once please explain the momentum conservation?
Momentum conservation. The idea is pretty simple. If it so happens that for a system of objects containing maybe more than one object, if the net external force is zero, if there is no external force, in that case, total momentum has to be conserved. In some cases, it may happen that the total external forces may not be zero, but in one particular direction, they might be zero. Okay. In this case, for example, I see that for these two together if I take as one system, what are the external forces? The external forces are gravity, which acts vertically, and the reaction from the ground, which also acts vertically. So there is no, because there is no friction, there is no net horizontal force acting on the system. External I'm talking about. Internal there are forces, but I'm talking about external forces. For this system of particles containing capital M, small m, there is no net external horizontal force, and therefore the momentum in the horizontal direction will remain conserved, which implies it will always be zero. Initially it was zero, there is no momentum to begin with, so it will always be zero actually. Okay, that's what meaning. So the idea is that we can just take up a system and try to see what are the external forces. Internal forces may be there, hardly matters. The momentum cannot be affected by the internal forces. It can only be affected by the external forces actually. Fine. So if the external forces are zero, then the momentum remains conserved, as simple as that. Okay, square root of which Wait a moment, Shubham. Let me check. Okay. Yeah, that seems to be correct. That's fine, Shubham. Okay. Anyone else has got it so far? Acha, you have to figure out the speed, isn't it? Same answer. 2 root over 2 GR. Pranjana, your M by capital M plus small m is outside. Root over of 2 GR. You applied it a bit wrongly here. I think you have just obtained the speed of the block of the point mass as root 2 GR. That is what I've taken. Pranjana. But that will be a bit wrong, in fact. The point is, had the wedge been stationary, then whatever potential loses will appear as kinetic energy. So then the speed will become root 2 GR for the block for the point mass A actually. But in this case, it is not so because as the particle comes down, it loses the potential energy. That same loss in potential energy provides the kinetic energy for both of them actually. So the speed of the small point mass at the bottom is no longer root over 2 GR, and that is why this is not okay. Yeah. The idea is to just consider the two velocities, which we do not know right now, for the wedge as well as for the point mass. They'll be definitely moving in the opposite direction because, as I said already, the entire system is a closed one horizontally. There's no net external force acting horizontally. Therefore, the total momentum must be zero. So if you just consider in this case, when this object reaches the bottom, it has a velocity, say small v. This is with respect to ground actually. With respect to ground is what I have. Ayurveda, okay, it's fine. This will be having a velocity this way, capital V. Both of them are with respect to ground, in fact. We are dealing with respect to ground, not the wedge. Okay. In fact, with respect to the wedge, the speed of this point mass will be something else, will be V minus capital V, in fact. And will be usual, this will be the bigger one. This will be larger, this will be smaller, depending on the mass actually. So first of all, the momentum conservation must come into picture because it's a closed system. And these velocities are assumed with respect to ground, okay? V and capital V, they're both with respect to the ground. Inertial reference frame is what I have. So in this case, first of all, the momentum conservation needs to be applied. We have in this case, therefore, MV must be capital MV because they are already opposite in direction. So we just need to make sure that the magnitudes are equal, as a result of which we have got this equation MV equal to capital MV. That's one thing. Small v is not known, capital V is not known. The next we have two unknowns therefore. So I require one more equation. The energy equation can be written down because we see that for the external system there is no work being done. Internally there is no dissipative force as well. Therefore the energy has to be conserved. Mechanical energy. If the mechanical energy is conserved, then I see that whatever has been a loss in potential energy, that must appear the kinetic energy for both of them, in fact, which implies that energy equation takes the form mgr for the loss in the potential energy, and that will be equal to the gain in the kinetic energy for both the objects. This must be therefore half into small mv square plus half capital M into capital V square. And because this equation I can eliminate small v, I can write down half m instead of small v, plug this one, capital M square capital V square by small m square plus half capital M into V square. And I can pull out in this case half capital M V square common. One of them cancels out. So what I end up getting is half, capital M by small m plus 1, which you could, Avibrata, it seems there's a mistake from the beginning. Arkodev, yes, what I said in this case is, it seems, Anak, are you getting the same result? I wanted to speed up the wedge. So, okay, let us see. Arkodev, what I said in this case is, I first, when we release the object, this entire system, oh, yes, Shubham, that's fine. Your school has started in the leave. We shall finish it after, around 7:30. Okay. In this case, as I was saying that as the small m is released from here, starts coming down, but you could see in this case that as it comes down over there, for example, over here, then there's a force acting on this object because the wedge in this direction. So it also exerts a force on the wedge a bit downwards, in fact, isn't it? It has a component in the forward direction, so that is it accelerates the entire thing. So what happens is as the block comes down, this will be in fact going that way over there till it reaches the lowest position, at which point the maximum speed, in fact, but subsequently as it starts going this way, now the force on the wedge will be that way. So you'll have a component backward, starts retarding, slowing down. So what happen actually, if you look at the motion of the entire system, will just come this way and this block will go that way. When it starts climbing this way, it slows down, again comes back. You keep on moving right and left, in fact, okay? If there's no friction. In reality, it will always stopping because there's always some friction in this case. Okay. So what I'm saying in this case is because of the fact that it's a closed system horizontally. In this system, there's no net external horizontal force. Therefore, the momentum must be conserved. So I assumed to begin with that whenever the particle A reaches the lowest position, the speed is small v, with respect to the ground actually, not with respect to the wedge, with respect to the ground, fine. And the speed of the wedge is capital V, fine. So I first conserve the momentum, small m into V for the smaller body, capital M to V for the wedge actually, they must be equal. The direction is already opposite, so we just need to make sure that the magnitudes are equal actually. That's the first equation. The second equation now comes from the energy conservation. The energy also remains conserved because the external forces work done on the system as a whole is 0, and there's no net dissipative force as well. There's no internal dissipative force. The energy is not getting lost. So if the energy is not lost, it must be the same always. So whatever has been decreased in the potential energy, whatever the system lost as potential energy, it must gain as kinetic energy. That is why I said we have the drop is mg capital R, in fact. That's the drop in the potential energy. And this must appear as the kinetic one. So I have equated half mv square plus half capital mv square. Okay. Now, because in this case we require the speed of the wedge, so I just wanted to eliminate small v. To eliminate small v, I just use the first equation. Write down instead of small v, capital mv by m. So that becomes the square of this. One of the m cancels out over there. I pull out half capital M. So one capital M by small m remains. There's just one over there. Fine. This gives us therefore half capital M V square into capital M plus small m by small m. That's what I get. From there, I could solve for capital V, the speed of the wedge. That can be solved from here. I just have twice mgr. This gives us 2 times mg capital R, in fact, by capital M appears and m by capital M plus small m appears. It seems that your answers are not okay, by the way. Abhiprata, that is not okay. Capital V square. So capital V will turn out to be root over of 2gr into small m by small m square by capital M plus small m over there. Okay. So So there's a mistake, I think. Oinak, your answer is not also correct. Chanjana already said. Shubham answer is also not okay. So none of the answers are correct so far, by the way. I think you made a mistake again. Well, it will be coming if I want the speed of the smaller block, but for the capital wedge, the bigger block, it is not correct. The answer says not what has been drawn so far. It is something else. The answer, in fact, is therefore. That's the required answer if I haven't made a mistake in this case. Okay. Is it fine? I mean, the point is that we'll have to kind of consider carefully the momentum and energy conditions. The requirement we know already. For momentum to be conserved, the requirement is that the external forces should be zero. And if it is not zero, look at in one direction, at least it should be zero. For momentum, the energy conservation, we require to have no external work being done, in addition to the fact that the internal dissipative forces must be zero. Okay? MCLI school has started. Okay. We don't have school today, isn't it? Yeah, just exam tomorrow, not today. I'll just give a couple of questions as the homework, and then you can leave today as well if you want to continue. Then the two questions specifically I would like to, three rather. Yes, Rishabh, you're saying something? I'm waiting.
Sir, in our school, we were doing gravitation, so I had a question from gravitation.
Okay, you can ask.
Sir, I cannot understand the concept of aerial velocity over there.
Aerial velocity implies the rate at which the area is being swept by the line joining the planet and the sun. Why? Okay, Rishabh, wait one moment. See, if we know already that the planets move around the sun in elliptical paths. So look at the aerial velocity. It will be nothing but the area which this line sweeps. This line, as the planet moves, the imaginary line joining the sun and the planet is going to sweep some area at some rate. The rate at which that area is being swept, that is the aerial velocity. It can be obtained quite easily. I mean, say if the angle is d theta, which is not very large, this is distance r, and practically it can be thought of as a circular arc. There will be an error, which will be this part, which is negligible actually. The area for this portion in a small time dt, if I consider, the area will be how much? It will be nothing but half into r square into d theta. I'm treating it roughly like a sector of a circle actually. Fine. So half a square into d theta has to be in radians. Therefore, the aerial velocity is this, which implies this half of r square into omega, the angular speed actually. Okay? This is the aerial velocity. The second law is saying the aerial velocity is constant, which is nothing but restatement of the angular momentum conservation actually. Is it fine?
Yes, sir, one more. So one more.
Huh.
Sir, whenever a particle does a motion according to the inverse square law, its trajectory is parabolic. So that one.
No, not parabolic. It's one of the conic sections.
Oh, sorry. Ellipse, sir.
Yes. It can be a parabola for zero energy, it can be an ellipse for a negative energy, and it will be a hyperbola for a positive energy. That's all.
The parabola for negative energy?
No, zero energy. Parabola for zero. Total energy. I mean, say total energy is zero. Total mechanical energy is zero. Then the trajectory is parabolic. If the total energy is negative, it is an ellipse or a circle. And if it is positive, it's a hyperbola.
That means they can be derived.
Yeah, definitely, it can be derived. but it's not required right now. But yes, we can derive it. Newton did that. Okay. Rishabh explained why we applied momentum conservation. The idea was pretty simple, Rishabh. I was able to apply the momentum conservation because the net external force was zero actually. That is why. We can always do that. Whenever the net external force is zero, the momentum of the system cannot be changed. Okay, it will always be conserved actually. Is it fine? No, and gravitation is not there in syllabus. She was just saying that she was being taught, so she has this question. Okay. Anything else? I will just wait. Okay, just take up a couple of questions and you can leave them. The first question you have is this. There is a pendulum bob of length L, mass M. It was initially at rest vertically hanging, and then a constant force F starts acting on the bob. F is a constant, both in magnitude and in direction. Or you might say there's a wind blowing, and the wind exerts a constant force between on the object in this case. Fine. So we have to figure out the maximum deflection. We need to obtain the maximum deflection of the pendulum bob. Okay, from the when I release it, what is the maximum deflection of the pendulum bob? That is what we will find out.
Arc length.
What? No, the maximum angle figured out.
Okay, sir.
Exam, Kudev, when is the exam for the rotation?
Yes, sir. From 3rd November onwards, it is starting. We have till that system of particles and rotational motion.
I shall see what I can do, by the way. Anna?
Okay, sir.
Chal, theek hai. I will say just take this question. Rest of which I just post later on. By the way, in case you have exam, so after you can leave today. Okay, we can look at this question some more later on maybe, or I just post in the group if you want. Nobody knows.